Welcome back. In the next part of this lecture, we'll be talking about zeros and roots and end behavior for polynomials. So to begin with, when we're talking about a polynomial's zeros, we are talking about the values of x that make the polynomial equal to 0. So if you've got a real number that when you put it in for x, it makes your function equal to 0, you would call that value for x a real 0 or a real root. So for example, if you have a function, f of x being f of x minus 1 times x plus 1, there would be two zeros. You would have a 0 of positive 1, and you would have a 0 of negative 1. If you put in positive 1 for x, that would make this all equal to 0. If you put in negative 1 for x, that would also make this all equal to 0. In other words, when we're talking about the zeros of a polynomial, we're talking about the x-coordinates for those x-intercepts. So there's actually a couple of ways that we could phrase it then. If you knew what a real 0 was for your function, then that means you know where the x-intercept is for that function. You also know that x equals c would be a solution to where is your function equal to 0. You also know that x minus c should be a factor. And that's, of course, not a surprise. When we said that for the last polynomial that I had, from this bracket, you would find a value of x being 1 as your 0, or as the x-coordinate for your x-intercept. And if x is equal to 1 is a 0, then x minus 1 happens to be a factor. That, of course, also means that if we were to take our polynomial and divide it by x minus 1, then it should go in evenly with no remainder. And so in general, if you know where a 0 is, then that means you happen to know what a factor is for that polynomial. And if you divide that polynomial by that factor, it should go in evenly with a remainder of 0. These last parts we're going to come back to, because later on we're going to be talking about factoring polynomials, and we'll be interested in taking polynomials that are bigger than just quadratics or degree 3 polynomials and coming up with all of the factors. And so that's actually going to play a role, that relationship between the zeros and the factors and the remainders. All right, so if we've got a polynomial function of degree 3 and the zeros are 1, negative 1, and 2, then one very easy answer that you could give would be the zeros are 1, negative 1, and 2, which means that x minus 1 needs to be a factor. That's where x equals to 1 would come from. X plus 1 would need to be a factor. That's where the x equals to negative 1 would come from. And x minus 2 is a factor because that would be where the x is equal to 2 would come from. And if you were to look at where is this polynomial equal to 0, you would find it's equal to 0 at 1, negative 1, and 2. You can also confirm that this would be a degree 3 polynomial. If you were to multiply this out and expand it, you would find that the highest power of x is 3. So this is a degree 3 polynomial. Now, the follow-up question for this is there more than one possible answer to the question of can you come up with a polynomial of degree 3 with these particular zeros? And if you're thinking about it for a minute, if you're thinking even about what we just did in the graphing in the previous video, we know that vertical stretches don't change the location of an x-intercept. So if we happen to know that this polynomial crosses the x-axis at 1, negative 1, and 2, it would still cross the x-axis at 1, negative 1, and 2 if we were to stretch things vertically, or if we were to flip things vertically. That would also stay with the same 3 x-intercepts. So if you're wondering, can we come up with a second polynomial with the same zeros that's also degree 3, the answer is yes, we can, and not just one of them, but infinitely many of them. So for example, if I were to take f of x and multiply it by 2, it would still have the 3 zeros of 1, negative 1, and 2, and it would still be a degree 3 polynomial. Or if I were to multiply everybody by -2, that would also have the same zeros and would also be degree 3, and so on and so on. So, yes, the answer is there more than one possible answer to this question? Yes, and not only is there more than one, there's infinitely many. Take whatever f of x that I have and multiply it by whatever your favorite constant is. That will give you another function with the same x-intercepts and with the same degree. So one other thing that's going to be important here for talking about how our graph of a polynomial looks like is talking about the multiplicity of these factors. If we wanted to talk about the multiplicity of a 0, we're talking about how often or how many times does that corresponding factor show up. So if you have, for example, a repeated 0, that happens when you have a factor that occurs more than once. And if you have a factor showing up n times and no further than that, then that factor, the 0 for it, has a multiplicity of n. So by that I mean, if we're looking at this polynomial f of x and you're wondering what are the zeros and what are the multiplicities, remember that the zeros come from looking at where is this polynomial equal to 0. And you'd find that there are 3 different values for where this polynomial is equal to 0. Either 3x squared is 0, which gives you that x is 0, or x minus 2 is 0, which gives you that x is 2, or 3x minus 1 is 0, which gives you that x is equal to 1/3. And so for these zeros have, for the first one, the multiplicity is 2. And the reason the multiplicity is 2 is because this solution, x equals to 0, came from a factor whose power was 2. So that factor of x wasn't just x, it was x squared, so that is multiplicity of 2. For the x being 2, that came from the factor x minus 2, and that only showed up once. So it wasn't x minus 2 squared or x minus 2 cubed, it was just x minus 2, so that has multiplicity of 1. And for the x being a third, that came from solving 3x minus 1 cubed equals to 0. And that factor shows up 3 times, so that means that that third has a multiplicity of 3. So this polynomial had 3 zeros, 0, 2, and 1/3. And some of them had a multiplicity of 2, some had a multiplicity of 1, and one of them had a multiplicity of 3. Now, the reason we're talking about multiplicity is because whether the multiplicity of a 0 is even or odd will tell us whether the graph of that polynomial will either cross through the x-axis at that 0, or whether that polynomial will touch the x-axis and bounce back at that 0. And it only depends on whether the multiplicity is even or odd. If you have a 0 with odd multiplicity, then you are going to cross through the axis at that x-intercept. If the 0 has an even multiplicity, then you're just going to touch and bounce back, but you won't cross through at that x-intercept. So if we're looking at this polynomial function, we can see for zeros that there are 3 different zeros. If we were looking for where is f of x equal to 0, you'd find that there's 3 solutions, that x is 5, or x is 6, or x is 7. Now, as far as multiplicity goes, the 0 of x being 5, that came from the bracket x minus 5, and that only showed up once. For x being 6, that came from the factor x minus 6 squared, so for that, the multiplicity is 2. For x being 7, that came from x minus 7 cubed, so the multiplicity is 3. And so now we can talk about the behavior at the x-axis. Remember that for the zeros where the multiplicity is odd, you're going to cross the x-axis there. So when x is 5 and when x is 7, for that graph, you would cross the x-axis. When it's even multiplicity, when x is 6, the multiplicity was 2, which is an even number. So at that point, we're just going to touch the x-axis, but not cross. So this has given us a good chunk of what we need to be able to graph a polynomial. Once we find our zeros and the multiplicities, we'll know what's happening at the x-intercepts, and we'll also know whether we're crossing the x-axis or just touching. There's still a couple of things left to figure out, however. And one of them is something that actually we won't be able to find, at least not in this class. And these are things called turning points. These would be the places in a polynomial where you would change from increasing to decreasing or vice versa. So we're talking about these points in our polynomial. These would also be the places where we have relative maximum and minimum values. Those would also be things that we'd like to know about. Unfortunately, except for parabolas, it's not easy for us to find those turning points. That's exactly the whole purpose of calculus. That's one of the things that calculus does, is locates those maximum and minimum values for functions. But for us, since we haven't learned calculus, and that means I'm not going to expect you to be able to find those turning points. So that means that when we're graphing our when we're graphing our polynomials rather, the only thing I can really expect you to graph would be the intercepts, those points, x-intercepts and y-intercepts, and what's happening at those, what's happening at the far left and the far right. But as far as turning points go, we won't be able to find where they are, which means that your graph and my graph and what the graph of the function might actually look like might differ slightly. So for example, if you happen to know that the graph crosses through the x-axis at both of these points, heading downward on both of these points, somewhere in between there's going to be a turning point. Is it here? Or could it be there? Or could it be there? All of those could be possible answers for how high up the turning point is or where the turning point happens to be. It also doesn't necessarily need to be directly in the middle of those two x-intercepts, because we're not talking about parabolas anymore. We're talking about polynomials in general. So unfortunately for us, we're not going to be able to find those turning points. But the upside is that you can't be expected to find those turning points. We just don't have the skills for them yet. So the last thing to talk about before we can graph any polynomials is the end behavior. And when I say the end behavior, I'm talking about what's the graph doing on the far left and on the far right. Because we already know what's happening in the middle. That's what the x-intercepts tell us. But what we need to know is, after we've left our last x-intercept, is the graph going to be heading up, or is the graph going to be heading downward? And interestingly enough, this is where power functions come into play. If we look at the leading term for our polynomial and look at that as a power function, whatever the end behavior would be for that power function, that would be the same end behavior for your polynomial. So for example, f of x, if you were looking at its leading term is 7x cubed. So the end behavior of my polynomial should be the same as the end behavior of 7x cubed. And we know what 7x cubed looks like. It goes up on one side and down on the other. So that means that for f of x, on the far right it's going up, and on the far left it must be heading downward. For g of x, same sort of an idea there. It has the leading term negative 2x to the 4, so that means the end behavior will be the same as the graph of y equals negative 2x to the 4. We know x to the 4 would look like a parabola opening up. Negative 2x to the 4 would look like a parabola opening downward. That would be y equals negative 2x to the 4. That means that for g of x then, it needs to have that same end behavior, going down on the far right and down on the far left. Now, we're going to be talking about factoring polynomials later on, and so at that point I'll give you a polynomial unfactored, and you'll need to be able to factor it to find its zeros. For right now, though, I'm giving you polynomials that are already factored to help us find the zeros, but that means we're going to need to know how to find the leading term, because of course the leading term will tell us the end behavior. We also need to know how to find the constant term, because the constant term, of course, tells us where our y-intercept would be. And now the nice thing is that for a factored polynomial, if you want to find the leading term, you just need to multiply together the leading terms for all the factors. And same sort of thing for a constant term. To find the constant term for a polynomial, multiply all the constant terms together for all the factors. So for f of x, our leading term I would find by multiplying all the leading terms for all of my factors. The first factor, the leading term is 3x. For the second factor, the leading term is x, but that factor is repeated. It's actually x minus 2 times x minus 2. So I have an x and another x. Same thing with the last factor, 3x plus 1. The leading term is 3x, but of course that factor is repeated twice, so it's really 3x times 3x. And then if I simplify that, I find it's 27x to the 5. So that means this is a degree 5 polynomial. That also tells us that if we were graphing f of x, it would have the same end behavior as x to the 5, 27x to the 5 rather, going up on the one side and going down on the other. Finding the constant term, same sort of thing. We're going to multiply together the constant terms for all of our factors. Negative 3 from the first factor, negative 2 from the second factor, which is squared, 1 from the last factor, which is squared, and that gives me negative 12. So this is telling me that we have the y-intercept 0, negative 12. That's the reason why I might want to know the constant term. Just going to do a couple more examples here. G of x, if we want to find the leading term for g of x, multiplying together the leading terms for all of our factors. So 4x, we have x to the 4, x, negative x cubed. And if we were to multiply all of this out, we would have negative 4x to the 9. Which means that if we were thinking in terms of end behavior for this polynomial, it would be going down on both. X to the 9. It would not be going down on both sides. It would be going down on one side and up on the other. 9's an odd number. There we go. That's better. And then if we wanted to know the constant term, again, same thing, we're multiplying together the constant terms for all of our factors. We do have to be a little careful here, because in this first factor, 4x, 4x is the same thing as 4x plus 0. The constant term for that first factor is 0. The second factor, the constant term is negative 1. The third factor, the constant term is negative 2. And in the last factor, the constant term is 3. that means that we would have a constant term of 0 for this polynomial. So that would let you know that the y-intercept should be 0, 0. In other words, this polynomial passes through the origin. And one more to do. Let's do this one, to finding our leading term, multiplying together the leading terms for all of our factors. And again, we have to be a little careful here because the first factor has only one thing in it, and that is the single number 3. And 3 then would be the leading term. That's a constant factor, and the leading term there is 3. In the second factor, the leading term is 2x. In the last factor, the leading term is x squared. And then now we just need to multiply that out, and that gives us 24x to the 5. For our constant term, same thing. Don't forget that this 3 is the constant term for the first factor. The second factor, the constant term is -2. And for the last factor, the constant term is 4. And that gives me a constant term of -96.